This conference will now be recorded.
Okay, so good afternoon, everyone, and welcome back to a fresh new session on market risk modeling. And we were talking about the basic functions, right? So we were kind of talking about some important functions, and we were exploring their applications into market risk modeling. So if I were to develop a mathematical, or if I were to develop a model, or explain a mathematical relationship, then these are the functions that we would be requiring. And two of the broad functions that we had talked about, one of them was the exponential function. The second was your logarithmic function. And we used that logarithmic function and that exponential function to see how is it that we can model explosive time series processes. How we can model explosive or mildly explosive asset price, or any kind of an asset price dynamics, right? So that is one that we had kind of studied, right? Okay, so now there are so basically there is another a very important explanation, or any very important application of this exponential function in uh, statistics, and that exponential function is used extensively in different areas of model development, especially for market risk model development. So that area that we are talking about, or that particular application that we are talking about, is the normal distribution, or the Gaussian distribution. Now we know that like when I talk about the Gaussian distributions, right? The Gaussian distributions are a very important source of it's a very important distribution, a very fundamental distribution in the domain of statistics, and has very widespread has very widespread applications, right? So if you have to define a stochastic process, which by default is the process for all market risk models, right? So for any kind of market risk variable, you see, you want to predict something, you want to model any element of stochasticity, you want to model the so you talk about the Black-Scholes-Martin model, you talk about the Raster model, you talk about any model in market risk, right? So it has to come, the business has to come from an element of stochasticity, and the way you model that stochasticity is mostly done using this normal distribution. So this normal distribution plays a very important role in talking about how exactly a stochastic element can be displayed. How exactly does stochasticity look like? How does the randomness look like, and so on, and so on. So these are some of the important. So this is an important area where we would generally see this functions being applied, right? So we'll define this function. We'll see how this exponential function is used. Right now, one at the crux of it, the exponential function, as we have seen, is used to model anything which is, or the exponential function itself is something which talks about about a gradual growth, right? So so from that perspective, so from there, right? So a few important areas that that we would kind of see over here is that what exactly are the application of the exponential function. So because normality talks about symmetricity, right? So therefore this function will play a very important role. Okay, so in modeling any kind of symmetry behavior, this exponential function actually plays a very important role, because one thing that we have seen is the sentiment that is associated with exponential functions is that you talk about constant growth rate, very uniform growth rate over a period of time. However, under some special cases, even this function can also be used to appropriate mathematical transformations to express the explosiveness of the variable as well. So there are a lot of different areas where this function can be used, right? So let us try to uh, show this, or let's try to see this particular part. Okay, so first of all, what we'll do is we'll define the Gaussian distribution, right? Let so this is a very specific way, this is a very typical way of defining a distribution. It says that let x be a random variable, right? Let x be a random variable, or let me put it like this: be a continuous real random variable, and let let mu be greater than 0, and similarly sigma greater than 0. Be two constants. Then the probability density function can be uh, okay, so then the probability density function of the normal distribution, or let me put it like this, of the Gaussian distribution can be defined as, so I'll go to insert, I'll put an equation here. So this is fx is equal to, guys, just give me a minute. Yeah, so as I was saying, right, so this is, so how am I defining this function? So this function is defined as, this is 1 divided by 2 pi sigma, e to the power of, this is 1 by 2, This is x minus mu by sigma whole square. Right. So this is how you define the probability density function of the normal distribution. So if now when will this hold? If x belongs to minus infinity to plus infinity, mu is greater than 0 and sigma greater than 0. So basically, if these conditions happen, then this is okay. Else, okay, so under this condition, this is the probability distribution function that you will have. Now, if it is not there, so if any of the above condition is not satisfied, the point over here is if any of the above conditions are not satisfied, then satisfied, then if any one of the conditions not satisfied, then fx is equal to 0. So for the probability density function to be defined, right, this function or this these conditions must be satisfied. That is, x must be real, mu must greater than 0 and sigma greater than 0. Now it is the square function, or the square of this function, which makes it an even function, because of the square, your fx and your f of minus x is always the same. So in this function, in this probability density function, f of x and f of minus x is always the same. So over here, f of x and f of minus x is always the same. Therefore, this probability density function, therefore this probability density function, or as we call it, the PDF, is an even function, and hence symmetric. So this is what broadly the function is. So this is the normal distribution. So one thing that you see is that you can use this, you use the exponential function to even describe the as concepts of normality, right? Okay, so before I move on, very quickly, can you just tell me what is the continuous? what is a random variable? What's a random variable? Because this concept of random variable is very central, like in any market risk or any credit risk, any model that you are developing, understanding this concept of random variable is absolutely very important. So what is this random variable? Yes, Shubham. Okay, so Swastik says any variable whose outcome is random. Okay, whose outcome is whose outcome of a random event. No, not really. Yes, Shubham. What is your point? I cannot hear you. Are you talking? Shubham, you are not audible. Okay, a random variable is a function. Okay, as in what type of a function? So y equal to fx, where x is random, so accordingly the system output y is also random in nature. No, not really. Yeah, so what you are trying to say, I mean, I'm getting the sense of what you are trying to say, but the question over here is the way you are saying it is wrong. So first of all, a variable cannot be a function, number one. Now, when you say x is random, right, and the output y is also random in nature, so that is something related to the function. Now, you cannot actually, if you are passing something to a function and you are getting a random output, so that means the function is random. Now the question is that when you are talking about a variable being random, what do you mean? So both of you are beating about the bush but not coming straight to the point. So Swastik says a variable is the variable which is the outcome of a random event. So both of you are talking about this random, but what you are not doing is you are not defining this random. The answer to this question is in defining the random. Yes. So how is it? So a random variable is a variable. Now, first of all, it's a variable, right? Now, given that it's a variable, it cannot be a function. So the nature of a variable is determined through the values that it generates. So let's say a variable x is there which generates values, let's say x1, x2, xn. And each of these n outcomes have a probability associated with it. only then is that variable said to be a random variable. So for example, you are tossing a coin. Your x is a variable which shows that there are two possible outcomes. Now, if both of the outcomes are sure to happen, then it's a sure event. Now, if there is a probability associated with each of the outcomes, then it becomes a random variable. So a random variable is a variable whose outcomes have a probability distribution associated with it. Now, if that's the thing, only then can you say that variable is random, and then only then can you introduce any kind of stochasticity into the behavior of that variable, right? Right. Okay. Now the next question that comes out over here is, so okay, so only then can you introduce any kind of stochasticity into this. Right? So now let's try to see that. So let's try to see what are the characteristics of this uh, probability distribution, right? The key characteristics of the of the normal distribution are okay. So let me put this. Number one, the expectation of this random variable x is mu. Is mu. Okay. So what is the implication of this result that I have written over here? So I'm saying that this means the mu, so the mean of the distribution, the normal distribution is mu. So what is the implication of this? So what is the implication of this particular measure over here? Yeah. So what is the implication of this measure, Mr. Roy Choudhury? Please do the honors in the chat box. Yes. What is the implication of this line? Expectation of x equals to mu. How will you interpret this line? This is the mathematical result, right, for a distribution. But how do you interpret this line? Swastik, Shubham, anyone can go ahead. You can put your answers on the chat box. I mean, in the chat box. Expectation is constant. Good. So, how would you interpret this? You are just 90% already in. How do you interpret this? So Swastik says expectation of most of the observations are around the mean. That's an implication. I mean, that's a implication of the data, or that's how you read the data. But over here, I'm asking you to read this result that we have obtained. So Shubham says the expectation is constant. That's fair enough. Yeah. So what is actually then the implication of this result? The implication of this result is that when you say the expectation is constant, a better way to say that, a better way to say this is, a better way to say this is that the that a normal distribution has a constant mean, right? Now, what is the difference between saying an expectation is constant and saying that uh, you know uh, so so over here the expectation over here is, so when I say the expectation of the variable is constant, right? So so it shows up, it talks about a moment. Now whenever I'm, so when I say that the mean of the distribution is constant, right, or it's a distribution which has a constant mean, the advantage of interpreting it in this way is it gives you some insights into the distribution, or it gives you some insights into the distribution. What does it do? So it tells you that if your data is to be symmetric, or if you want to test whether the your data is symmetric, then you more or less must have a constant mean. And this is the reason as to why, when we talk about time series data, so we say that if your distribution, or if the values of if the behavior of the variable over time is not very symmetric in nature, then your means will keep on changing from one part to another. So if your error terms, so when you're trying to assess whether your error terms are random or not, if the mean is not constant, then you know that there are problems affecting the error, because if the variance of the error is changing, like in the case of heteroscedasticity, what it also implicitly implies is that the mean is also changing, right? The mean is also changing. So that's how, that's how this moment or this result is important, right? So basically this is the very important check that we generally do for the result, for this for a to assess if the distribution is symmetric or not. The first thing you check is, if I take certain subsamples of a distribution, the mean should be more or less constant. So as you identified, Swastik, that most of the observations, if I take multiple subsamples, for most of the samples, the mean that I will get will be more or less constant around that long run behavior, around this mean. So whatever mu you would get, and the mu that you get from the various samples, will be a value which is fluctuating around this mu. So that is why this result is important. Now this result is important to assess the symmetricity of a data, because if you take a data sample and you calculate a mean, you will get a constant value. But if I am using multiple samples, or if I use a distribution of the samples, right, then the mean would, or the sample means that fluctuate around this, or would be something around this mu itself. So if my sample is symmetric, no matter from where, whichever part I pull out my data, right, from whichever part I start pulling out my data, I will always have this element of homogeneity, and hence the mean will be always close to that overall sample mean. Because, and what ensures that it happens, what ensures is this, that there is an element, underlying homogeneity assumption of this distribution. So if your distribution is symmetric, what it means is that the set of record that you have is very homogeneous in its behavior. It's very homogeneous in its patterns, right? So that is why this result is important. So it says that the symmetric asymmetric distribution, asymmetric distribution has a constant mean. So if a distribution is seen to exhibit fluctuations in the mean value across multiple subsamples or subsamples ordered over time, then the distribution of the variable is considered to be asymmetric. So it is considered to be asymmetric. So this is one of the important checks to see whether a distribution is more or less symmetric in nature or not. And that is to check that the first check is to see whether the mean is constant. So similar, so this a similar extension of this principle is seen in the concept of stationarity, right? Because if your subsamples are different, now what makes a subsample different across time? So what makes it different is the presence of seasonality, the trends, etc. So it may be present in a part of the data and not in other parts of the data. It's a specific part of the data but not present in the other part of the data. So that's where you try to look into it. Right. So being okay, so over here, so if a distribution is seen to exhibit fluctuations in the mean value across multiple subsamples or subsamples ordered over time, then the distribution of that variable is considered to be asymmetric. Okay. Now the next question, so the next characteristic that comes out over here is that okay, so the next thing that we have over here is that the variance over here of this distribution is also constant, right? So what is the interpretation of this? So the interpretation of this part is that that the the fluctuations are very regular. So if your distribution is symmetric and things are very homogeneous, so the fluctuation that you will observe at one part of the data will be a similar fluctuation that you observe in the other parts of the data, right? So for a now, if the fluctuations are varying at times, now think about a stock market. Your fluctuation from the mean value is different at different parts. The more volatile your market gets, the more it happens. The less volatile your market gets, the lower are the fluctuations, the closer are the fluctuations, lower are the oscillations. So that is another part of riskiness. So that's another part of this risk. So whenever we are trying to kind of get this, so one of the things which always remain over here is that this moment, so one of the most one of the most romantic aspects of a Gaussian distribution is this constant mean and the constant variance. So through this it justifies the underlying homogeneity in the data. So the oscillations about the mean is always very uniform. The mean itself is very uniform. It's not a very volatile situation. Now, if that happens, then there is an issue. So just think about it. You are talking about a random movement, right? So how does a random movement work? So in a random movement, your mean is 0 and your standard deviation is constant. So you have a constant deviation, right? The mean is 0. So about 0, you are just having some fluctuations. So if you plot it, it's just a zigzag all across. You cannot actually capture a specific, any specific pattern. So there is a whole sense of a stability, of homogeneity right across. So every movement in a random space. So any random movement is an element of homogeneity, right? So explained right throughout. So therefore, you cannot, or there is no way that you can capture this thing. So that's what it is, right? So let's get so the two most important characteristics of a normal distribution, once again, is a constant mean and a constant standard deviation, right? So basically this point says has a constant standard deviation, has a constant standard deviation. So if a distribution is seen to exhibit fluctuations in the standard deviation, in the standard deviation, then across multiple subsamples, then the distribution of the variable is considered to be volatile or subsamples ordered over time. The distribution of the variable is considered to be volatile. So these are the two most important characteristics of a normal distribution. Right now, apart from this, the normal, so there is another thing that the mean, the median, and the mode is also equal to mu. Right. So because the distribution is symmetric, so therefore the expectations of x is equal to the median of x is equal to the mode of x is equal to mu. Okay. Okay, so expectation of mean, median, and mode. So this shows that this is the condition for symmetry. Symmetry of a distribution. So this is what is the basic idea about the normal distribution. So one thing that we have seen till now is the way we can use the exponential functions to define more than exponential movements, and the way we can use this exponential functions to define like symmetric movements, right? So now let us very simple, very easily, let's write the next step will be to plot this distribution and observe the simulations and see how these simulations would work. Right. Okay. So let's have a look into the simulations. Okay. So over here, if you see this, so this is how a symmetric distribution would look like, right? So I have the values over here, the values of the variables, and I have the normal distribution. So basically, to plot this normal function, what we have done is we have either taken the value, right, and the mean of this distribution, the standard deviation of the distribution, and put it at false. Okay, so over here, what we'll do is we'll take this graph and let's quickly plot this. So let me just select the data. This is normal function. This is the value. Okay, so so what we have done is we have plotted this graph, right? So we have plotted this distribution. So I think it will be better if we plot. So over here, what one thing that I can clearly see is that this distribution is a very symmetric distribution, right? So let's just plot, let's just pull this out over here. So this is figure 7. Figure 07. Okay, so figure 7. So this is a plot of the normal distribution. Okay, so over here we have the values of the x variable. The x variable. And over here what I have is the y variable. Right. So over here, so this is how your normal plot would look like. Okay. Now the next question is, so over here, so from here I can clearly see that symmetricity over here. Now if you want to check for the mean, median and the mode thing, right? So we have the average over here. I'll just write the average. Sorry, this is the sum plot. Okay, so this is the sum product over here is the mean. The mean is 0, right? So now the next is what I'll have is the median. The median is this value. The median is 0, and so will the mode. Right. So the mode over here occurs as at 0 because one thing you can see the highest percentage is or the highest relative frequency, the probability distribution is corresponding to this 0 over here. So one thing that we can clearly see the mean, median, and the mode all occur at 0 for this distribution, and hence this distribution is considered to be a very symmetric distribution. Right. Now, having talked about this normal distribution and all, right, having talked about this, uh, okay, so now one of the important thing is the next thing that we talk about over here is that how do we apply or what are the applications of this normal distribution in this domain of stochasticity, and how do we model the stochasticity using these using this probability distribution. Right. So let's get started. So what are the applications? The two core applications that we'll talk about are number one is the white noise error term, and the second that I'll talk about over here is the Weiner process, right? So how does this? So what exactly is this white noise error term, and how does it affect a certain model, right? So how does it affect the existence of an equilibrium and stuff like that? So that's the part that we will talk about in today's discussion, right? So I'll come to the mathematical modeling of this white noise error term a little later, right? So, but before I go into that, let's see some simple Excel simulations to understand how this white noise error term uh, becomes in handy, and then we'll see what are the implications that this white noise error term would have from the view of the point of view of the model development exercises, right? So let's get started with this. Now, so if I'm talking about the white noise error term, I'll have to talk about the white noise simulation, right? So what exactly is a white noise, and how does that work, and how does that white noise go ahead, and how does it start impact the pure equilibrium of a system? And this white noise is one of the most important applications that you will always come across. You would always see, and a pure white noise process, a pure white noise process is generally observed in so you do get to see some of them in the financial markets, in a market which is driven by speculation, right? So in a subject which is driven by which is totally driven by speculation, hardly any fundamentals to play, and so think about it like this, right? Let's say let's say you have bitcoins, right? And with this new idea, so this bitcoin is a new idea, right? So the idea which talks about idea of cryptocurrencies, blockchains, and that entire domain. So you know that, okay, this can actually revolutionize the payment structure up to a point of time, right? So after a point of time, so this asset would start increasing. So everyone is just going gaga. But the question is, does this Bitcoin have any fundamental binding? Does it have all the necessary characteristics of that of a currency? So the moment you talk about trading into bitcoins, and like, when I see, like, Shubham making millions out of trading in bitcoin, I would also try to run after making that million. So when I am running after that millions. I am not running after the trading logic or that information that perhaps Shubham is using to make those millions. So so I kind of run behind that. So seeing me 10 more people run. So what creates this random walk process, and what creates this entire domain of speculation in any kind of asset, right, is the fear of missing out, and which that leads to herd tendencies, and that leads to creating so that leads to creating asset price instabilities, or instability in any one of them, in these market variables, thereby leading to a whole new set of risks. So that's the part that we need to talk about, and that's where a random walk type of a unit root type of a walk comes in. And this random walk is an extremely useful technique to explain, in order to understand the basics of uh, a non-stationary time series leading to a mildly explosive time series, and thereby leading to the prediction side of it. So there are a lot of different things which goes into this, right? So over here, so we first introduce ourselves to this concept of white noise. We'll see how this plot actually comes in. So what I do over here is, in this first one that you can see, I start off with an initial condition of 5. Right. So I assume that my variable, the variable that I have with me, uh, takes a value 5. It starts off at 5. And from there, what happens is it keeps on increasing. So time keeps on increasing. Now this variable, so what I have done over here is, I have put out a, I have kind of put out a so what I've done over here is, I have kind of put out a very stable system. So the stable system over here is, it starts with so in the first period, it starts off with 5. The next period, it takes a value 5, right? Then again, in the next month, it takes the value 5. So it keeps on staying at 5. So it does not move from 5. So this is a very stable equilibrium situation that I have, right? And it all goes, and whatever it was in the initial part, it keeps on going on till now. So over here, what I have first created is, I've created a plot of y. So y is over time. So what I have seen is, how is it that this yd varies over a point of time, right? And over here, I have all these serial numbers and all these concepts. Now over here, in this next part, what I have is the scatter plot. So in the scatter plot, what have I done? I have just seen how yt and yt minus 1 evolve with each other. So that's what I have seen. Right. Now, when I look into this, okay, so over here, what I see is that if I do a scatter plot, I see at one point of an equilibrium. So my equilibrium point doesn't change too much. Right? So over here, you see that this point remains where it is. yt and yt minus all have the same point, and it's a point equilibrium. Now the next thing that I just do is, right, the next thing that I do over here is I just bring in a random component. So what is this random component? This random component is generated from the normal distribution. I just generated a set of random points. Just generated a set of random points over here, right? Now these random points will be anything between plus and minus and all this. And the way these values keep on changing, right? You see how your noise range change. Okay, so over here, what I have seen is that as your numbers are increasing, right? So how does this noise move over time? Right. So the scatter plot that I have done, this is the scatter. So I've plotted the graph over here, and also I've done a scatter plot because I wanted to see how this random movement looks like. These are random points which are generated from the probability distribution. So just have a look over here. Can you say that this has any specific trend? Can you say that okay, this has a positive trend, a negative trend, or whatever it is? You cannot say, right? So because this is absolutely random in nature. And what is that variable which generates this? So it is generated with a mean of 0 and a constant variance, right? Okay. So now what happens over here is the following. So over here, if you see, let's say I just change this. So this overall it changes over here. So there is no specific pattern, and you can see how it changes. Now come to the next part. So this is the table 1 simulation without the random term. So first of all, you have the values that I have over here. Right, and so the initial value is 5, and I have 4.22. This value change moves to 4.22 over here. From there, a random value is generated, moves to this. Then you go. Then again, a value is added. So over here, I have the random generation happening. With that random term, this is how my series looks. Right. So this is how my series looks like. So I don't have a you know. So I kind of don't have a very so over here I don't have a control over what the values are, right? So the only point that I have in my control is the initial time point. Now from there onwards, the way whatever way this is changing and whatever way these variables are evolving, right, I do not have a control over that. Okay. Okay, so over here, so this is so this is how a white noise random error term or a white noise looks like. Now imagine the element of uncertainty, the element of stochasticity that this value brings into the equation. So basically, this was a very basic difference equation, which we saw in table 1. Now from table 1 to table 3, the thing totally changed just because of the incorporation of these random components. Right. So this is one possible way through which. So this is that randomness which you cannot predict, and it is this randomness which causes your actual values to deviate from your predicted values, right? And this is the amount of turmoil it can actually cause in your system. So this is one way through which you incorporate your you incorporate the white noise into, or an element of riskiness into your system, right? So that's how, so that's what the thing is. So this is one possible way. So the next step over here is to mathematically specify this white noise, study its property, and talk about the random, or rather, talk about the the random walk process, the random walk, or as we call it, to talk of the random walk hypothesis, its impact on time series models and on any end set of econometric models which you may use to model or to estimate the risk that is there in a market risk variable, right? So be it a foreign exchange trajectory, or be it a interest rate trajectory, whatever it is. And if you're trying to predict that, you are trying to find out the order of the order of the time series model or something of the sort. That's where, whenever you are trying to predict that, that's where this result actually comes in. Right. So this is how you can actually simulate a basic white noise model. The next question that comes over here is that how to specify this mathematically and see how it's applied. And the second and the most important concept that we talk about over here is the Weiner process. So the Weiner process forms the very basic, or the very fundamentals of your stochastic calculus, right? So these are the two parts that we discussed in tomorrow's session. Tomorrow's session will start from 3:30 p.m. in the afternoon, and we'll kind of do it till 5:30 p.m. tomorrow, right? Okay, so let's regroup tomorrow, and let's do this part of white noise and the Weiner process. So basically, the flow of the discussion that I want to take up over here is to start from the point of so basically started from function, and then go and see what are the key applications that we have for different part of the functions, right? So especially the most critical asset price equation, because once we have this part, right, so that's where we start talking about the Black-Scholes-Martin model equation and Hidalgo's lemma, and from there, so so as I go to solve some of these lemmas and some of these problems, so that's where we talk about derivatives, limits, continuity, and so on, right? So we'll see how these assumptions, or these basics of mathematical theory, help us in framing some of the key theories of finance. So one of them will be the Kaplan model. Another of them will be your Black-Scholes-Martin model, and the another will be the volatility model, the volatility framework. And then from there we explore different market assets, and we'll see how is it that risk is created in each of them, right? So that will be kind of the flow of the discussion. So let's try to regroup tomorrow, right? Let's not stress ourselves too much. So let's regroup tomorrow at 3:30 p.m. and from there we'll take it up. Thank you.